so let's get started with the third video in this series, which is going to be on intracellular adhesions and other junctions. So, intracellular So in this video, we'll be talking about how cells are connected to other cells or connected to their ECM through different junctions, and what are the functions of these junctions. So we'll be looking at 5 of the most common type of junctions that you'll come across in your pathway of studying medicine. And these would be your tight junctions, adherents junctions, desmosomes, gap junctions, and hemidesmosomes. Hemidesmosomes we've already come across in our previous video. And right now we'll be discussing them from top to bottom. So we'll be starting from the apical domain down towards the basal domain right here. So this would be your apical domain. So first off, we have the tight junctions. Let's zoom in a little bit. All right. So tight junctions are the nearmost junctions to the apical domain right here. So these are present on the lateral surface, and these are the nearmost to the apical domain. Therefore, we discuss them first. And what they do is that they tightly closed the gaps between two cells. So we've got a cell here, and we've got this cell here, and they close the gap between these two cells, so nothing can come across from the apical site between these two gaps. So they tightly bind the intracellular passage to prevent the entrance of any molecules that may come from the apical domain between the intracellular passage. And these junctions are made up of important proteins called claudin and occludin. So claudin, occludins, and therefore these are also called zonula occludins. This is another name for the tight junctions, zonula occludins. And these proteins make up the tight junction, which is internally connected to the cytoskeleton of the cell. So we've got actin filaments over here. This is going to be actin internally, and it is connected, the tight junction is connected to actin, and as we can see here, that it also spans the cell. Maybe use another color. Okay, as you can see here, it spans the cell as well. So this junction has two characteristics. It's connected to actin, and it spans the cell. All right, and it is made up of claudin and occludins. Therefore, they're also called zonula occludins. That's it. All right, so number 2, as we move from the apical domain downwards, after the tight junction is adherents junction. All right, and adherents junction, as the name suggests, to adhere, basically to anchor or to link or to bond. So these provide linkage and stability between the two cells. So for example, this cell here and this cell here, this junction right here, which is the adherents junction, will provide linkage between the two cells. All right, and these junctions are made up of proteins called E-cadherin. One of the important proteins that is found in adherents junction is E-cadherin. You may need to remember this name because this plays a role in pathology later. And the other protein is called catenins. All right. And as we discussed, that these proteins, when they make up the adherents junction, they provide linkage and stability between the two cells. Another name for the adherents junction is zonula adherents. Very easy to remember because over here we discuss zonula occludins, and it contains the occludin protein. So zonula adherents, as it is the adherents junction. Internally, they're also very easy to remember because they have the same features as the tight junction. They are internally connected to the actin filaments. Okay, and they span the cell. Let me write that down. Span the cell. So you may need to remember these features. They're connected with actin, and they span the cell. Now, a clinical correlate to the adherence junctions would be something like the EMT. EMT is, if you study cancer, you will learn that it is the epithelial to mesenchymal transition. Epithelial to mesenchymal transition. So basically what happens for example, in carcinomas are the cancer of the epithelial tissue. What happens is that these E-cadherin proteins, these may be lost, or they're either mutated or degraded, and this results in loss of adherence junctions right here. So there's no linkage and stability, and the cell, for example, this cell right here, would be allowed to escape from the epithelial tissue and become mesenchymal. And this is the epithelial to mesenchymal transition, and this may lead to metastasis because the cell escapes the epithelia and it can move to other tissues, for example, through maybe blood vessels that may be present around the tumor. Okay. Just like the zonular adherence or the adherence junction, we also have another type of anchoring junction, and those are the desmosomes. All right, and these desmosomes also contain cadherin family proteins. So they also contain cadherin, and these may be desmoglin, okay, or desmocolin. These are proteins that are present inside these anchoring junctions, okay, and they help in intracellular linkage and stability. So they help in the linkage between this cell and this cell, just like the adherence junctions. But the difference between desmosomes and adherence junction is that these are connected internally to intermediate filaments. Remember, adherence junctions were connected to actin filaments, but these are connected to intermediate filaments. And as you can see clearly that these also do not span the cell. Unlike over here in the adherence junction, these span the cell, but these do not span the cell. Okay, so these two differences. They contain intermediate filaments instead of actin filaments, and they do not span the cell, just like unlike the adherence junctions. All right, so next up would be gap junctions right here, but I'm just going to skip those for a while and jump to hemidesmosomes, because we've just done desmosomes right here, and I'm going to skip to hemidesmosomes now. Hemidesmosomes, we've come across it when we were studying in the previous lectures, that these are present at the basal surface, and they contain proteins called integrins that allow the cell to bind to the extracellular matrix, the basement membrane that contains laminin, and these bind together and provide cell linkage and cell stability. And as you can see here, it is connected to the intermediate filaments again. Not very important to know though. But an important clinical correlate would be skin blistering disorder. Now, this is a disorder which results from a mutation in beta integrin. And this mutation can lead to skin blistering disorders. Also called epidermolysis bullosa. And now finally we move on to the last in the series, our fifth junction. This is called the gap junction, also called the communicating junction, as it allows communication between two cells. Gap junction is a kind of junction that I consider as the most important out of the five, because we discuss them when we study physiology and embryology and pathology. But as far as the histology is concerned, these junctions are responsible for communication between two cells, and they allow a certain things, for example, may be processed in this cell to go to this cell, and allows signaling through this way. And these junctions are made up of channel proteins. These channel proteins are called connexins. Okay, and these join up to form connexons, which are the channels through which the molecules pass through. And a good example of these gap junctions would be, for example, in the embryo mesenchyme, where, as we know, that there are no hormones through the endocrine system usually, and therefore in the early embryo especially, the cells are dependent on intracellular communication, and this is done through these gap junctions. A very common example would be, for example, the JAG1 gap junctions that are present in the embryo mesenchyme. Another example would be, for example, in the heart muscle. So cardiac muscle has intercalated discs. When we study cardiac muscle later on in the series, we will discuss over the specifics of what makes a cardiac muscle and how the intercalated discs are play their part. But for now, it is enough to know that the cardiac muscle, for example, let me just draw that here. So for example, we have some cardiac muscle here. These are mononucleated, and these would be your intercalated discs that are attached to each other, and these contain the gap junctions that allow intercellular communication and allow a rhythmic contraction. You will study more of this in physiology for sure. And that sums it up. So, so far what we have discussed or studied is that the intercellular adhesions and other junctions, there are 5 major types that we have discussed: the tight junctions, adherence junctions, desmosomes, hemidesmosomes, and gap junctions, and all of their roles that we've studied. So let's move on to our neat notes here. And I'm just gonna read them quickly for you. Intercellular adhesion and other junctions, tight junctions, zonular occludins. Remember, we discussed that they contain occludin proteins right here, and therefore their name is zonular occludins. And near apical surface, so these are the nearmost to the apical surface and made of collagen occludin, connect to actin filaments that we studied here. They connect to actin filaments and span the cell. All right, tightly bind intercellular passage to prevent entrance of molecules. So they prevent anything from coming between the intercellular pathway. And then adherence junctions, zonular adherents. These contain cadherin proteins, and they perform the function of adherence. And they're also connected to actin filaments, and they also span the cell. Now, desmosomes, we studied cadherin family proteins, desmoglein, desmocholine connect to intermediate filaments, do not span or encircle the cell. So they do not span the cell, but they are also connected to intermediate filaments. And then we studied the hemidesmosomes in the basal surface. And finally, we went over the gap junctions that allow the transmembrane intracellular communication. And they contain proteins called connexins, connexon. A good example of this would be the intercalated discs in cardiac muscle, or JAG1 in embryo mesenchyme. All right, that's it for this video.